My name is Sester, and I want to talk about a deep learning approach to data-driven model-free pricing and to martingale optimal transport, which is joint work with Ariel Neufeld from NTU Singapore. And our goal here is to present an algorithm which allows the efficient determination of model-free price bounds. We do not assume any underlying model for a whole class of exotic derivatives, possibly depending on a multiple number of underlying securities. As a canonical example, which we will always consider, we introduce the class of basket options, which are parameterized by theta, which can here be associated with the weights in the sum of the payoff, and the strike L for the whole weighted sum of the underlying securities. And the idea of our approach is to consider market parameters, which I will present in the next slide, what they are exactly, and the theta, which is associated to the specific payoff in the class of payoffs we consider. This is the input to our approach. And given this data, we compute some model-free price bounds, lower price bounds, and upper price bounds. There are several works dedicated to this, so we assume we know how we can compute these price bounds. This precise algorithm already exists. We do this a lot of times, and then we let a neural network learn the relation between these inputs and the lower and upper price bound. And then we obtain a trained neural network, which allows the very fast and very efficient, as we will show, computation of lower and upper price bounds, model-free, given some input parameters, and this can happen then online in the end. To compute the lower and upper price bound, we consider a super and sub hedging approach, and the prices of these super and sub hedges then correspond to the lower and upper price bound. And to this end, we consider semi-static trading strategies, and the payoff of these trading strategies are given by cash position A plus some investment in call options and put options, and in a self-financing trading strategy where the payoff is reduced by proportional transaction costs. And we also take into account bid and ask prices indicated by the super index plus and minus respectively. And we measure the costs for setting up such a semi-static trading position. And given some bid and ask prices, which we denote by bold pi, they are given by the cash position A plus the price for buying the call options and buying the put options respectively. So the sum of all this is what we refer to as the costs of the trading strategy. And then what we want to compute is the minimal super hedging price and also the sub hedging price to obtain the lower bound. But here for the upper bound, the super hedging price is given by the minimal costs of such a semi-static trading strategy for among all those strategies which super replicate some payoff phi and given some constraints. So we assume that this super replication property holds on the whole space. So this is model free indeed, but the space is reduced to a compact interval. So the upper bound can be arbitrarily large, but there exists an upper bound for the price pass. And also we assume the positions which we invest in the call and put options and the self-financing trading strategy are bounded by another boundary B. So this sigma refers to the sum of all positions. We assume we are given these parameters which bound the problem, and we assume the class of payoffs, which we consider as a class of continuous functions, and we assume that the relation between theta and the payoff function in the class of payoff functions is continuous. Then we obtain that the relation between all the input parameters, which are the strikes of the put and call options, which are the bid and ask prices of the put and call options, which are the respective spot prices of all of the underlying securities, and theta, which is associated to the specific payoff function. The relation between these inputs and lower price bound and upper price bound is continuous. This allows to use the universal approximation property of neural networks to approximate lower and upper price bounds by a neural network, which depends on the previously introduced inputs. And this neural network is then close to the lower and upper price bound, arbitrarily close, as we can show in this theorem. And this allows to train a neural network in praxis, as we show in this example, where we consider two assets and the class of basket options written on these two assets. And what we do in this example is to consider the S&P 500 in June 2020, where we observed put and call option bid and ask prices for all of the constituents of the S&P 500. Which we use as an input to compute with another algorithm, lower and upper price bounds. So not by the neural network, but by another algorithm which exists, for more details, I refer to our paper where we give all the details, which algorithm we use and so on. And we compute these lower and upper price bounds for a lot of different weights, a lot of different strikes L, and for all of the different prices we consider for different constituents. So we consider pairwise different constituents, and in total we obtain 150,000 samples of this methodology, which we then use to train the neural network. And we test the neural network on data having the same structure, but in contrast to the training data, the testing data was observed in August 2020, so 2 months later. And we have 10,000 samples to test the trained neural network on. And what we obtain is the following. We obtain a quite good accuracy, meaning that the true values which are given by lower and upper price bound, both are indicated here, can be seen on the x-axis, and the predictions can be seen on the y-axis. Predictions refer to the output of the neural network. And what we see is that the predictions are quite close to the true price bounds, which we computed before. And the scale is just divided by the weighted sum of the strikes to obtain some values between 0 and 1. And similar things can be seen in the histogram, that indicating that the prediction error is remarkably small in this case. This methodology can also be extended to the prediction of optimal super hedging strategies and sub hedging strategies in the case that we can uniquely predict such strategies. And also we can extend this methodology to the martingale optimal transport case, where we don't have put and call option bid and ask prices as an input, but rather marginal distributions. And we also prove that in this setting, we have a similar continuity result and can approximate the price bounds by a similar approach. And what we also provide evidence for is that our approach works even when we consider a large number of assets. We have shown that it works for 30 assets. Of course, in this case, the computation of the lower and upper price bounds by which we need for the training data needs a lot of time. And in this case, the trained neural network becomes even more efficient because the contrast the contrast in time efficiency with respect to existing algorithms is even larger. Thank you for listening to this talk, and I really warmly recommend to have a look in our preprint, which is freely available on arXiv. Thank you very much.